Hi there all. Today's video is about testing the resistances of the various carbons. I have 6 carbons and a base carbon. The base carbon will be this one here, chemicarb. It's an aquarium filter carbon, or I should say activated charcoal. And I lost my resistance tester with the bolts screwed into each end from, I don't know where that went, so I had to make up a PVC pipe piece with a piece of copper at the bottom, some little pads at the top there. I may or may not use a larger piece on top of that just to keep it all compressed, and we'll do various resistance tests. This is about 20 mil in height and about 16 or something in the diameter. I'll measure it. Here we go. Alright, the diameter of that PVC pipe is 25 and the height is 20. Alright, so I'll just loosely pack that as much as activated charcoal I could get in there. And for the base resistance, I'll just try it without the covering and see if that sort of works. I think it gets better if this is on there. So, aquarium activated charcoal, we're looking around about 3.5 in resistance, just loosely packed, so that will be our base resistance. And I'll move on to our carbon tests. We have some wood, which is at 1000 degrees in a metal crucible. We have some tomato plant carbon. That's the stem of a tomato plant. We have some feather carbon in a ceramic or a cement container. We have feather carbon in a metal crucible. And we have some of that wonder material, or whatever the material is, it's unknown, what grows on the outside of the container. And also some shop bought charcoal for cooking charcoal. That's the stuff we activated sort of with the urea and the feather carbons. So for our base resistance again, see if we can get better than 3.5. Sort of loosely packed, you'd probably need to pack it tighter. Alright, there we go, we got 2, it's gonna fluctuate. Alright, 3.13. Alright, we have 3, we'll say, for the resistance on our base shop bought activated charcoal. And I'll get back with the next. Okay, back. This is the stuff that grows on the sidewall of the metal crucible. One of the videos is a wonder material one. It catches on fire quite easy. It's highly attracted to magnets. Like just that slight amount there can hold that bunch of magnets to the plastic with a bit of force. Actually, see, it's really strong. I don't even think a piece of metal would be that sort of tough. So it has that as its property. It's highly attracted to magnets. It's sort of shaped like this. When it comes out, little flakes, they crush up into a sort of average size particle. It takes a bit to get those flatter pieces crushed because you have to impact it and break it. You could probably put it in a ball mill and it would mill up really well. And for its resistance, we have a resistance on this one. May not be packing down. Okay, it seems to be a bit high in resistance, sort of. So we're looking at 67 ohms in resistance on that material. Might not be packed, but I think that's quite packed. I'm pressing weight on it, but try that. Alright, that was alright anyway. So 68 ohms on that one. And the next one will be a feather carbon in the metal crucible. So I'll get back with that one. Okay, we're back with the feather carbon. It somewhat resembles this shiny material when it comes out of the furnace. This is in the metal container crucible. It's the particle size is a lot smaller, or this chunk size, it only comes out in little chunks this big. Sounds quite metallic like when dropped. Very shiny. That's a bit dull shine, but that's a shiny shine on the crusty outer layer. So for its resistance, is quite good. It's actually less than the shop bought activated carbon, sitting at 2 ohms. 2.1 ohm, 2 ohms. So that's looking pretty good. So feather carbon in metal crucible is actually better than the material that grows on the outside in resistance. So that may not be metals anyway. Alright, and the next one will be a feather carbon in a cement crucible. Okay, this is the second lot of feather carbon. This one was more of a controlled burn over 26 hours. It was at 200 degrees for 24 hours in a cement crucible, and then for the last 2 hours at 800 degrees. And the yield is slightly higher, and it forms larger sections of the material, which for a resistance test on the base material, depends on how hard you press, around about 38 ohms. But in our little test resistance chamber, it needs to be packed a bit more, I think. Hang on, I'll pack that. That's collapsing too much. I'll be back. Yeah, I think I have it packed a bit better. So for the resistance on this cement crucible version of the feather carbon, at a lower temperature, someone's not getting a good reading. Okay, the resistance seems to be higher on the less heated form of the carbon. Or it's not compacting properly. Not sure what's going on there. At this rate, seems to be a higher resistance reading than the metal crucible, which is at a higher temperature. So perhaps higher temperature is good, but your yield is down. This one's sort of collapsing in on itself. Alright, so it doesn't pack quite as well as the other one maybe. I didn't have that trouble with the other one. So high resistance on the slowly cooked stuff, which is unusual. Alright, so gives the larger results, but the end product isn't quite as good. Perhaps I needed to take the temperature up higher on the last two hours of the stage. It's not as shiny on that side, but it's quite shiny-ish through there. One could say that's almost like a feather structure. Alright, our next carbon will be the tomato plant. Okay, the tomato plant stem actually looks like that. Sounds a bit... It's not as shiny. Shrinks down to size, that was like that. And for its resistance, oh, that's sinking. No, I'll have to repack that as well. I thought I was packing it, but sunk. I'll be back. Okay, tomato plant, take 2. Hopefully I got it packed enough. Okay, we're looking at 13 ohms for the tomato plant, which is an increase on that low cooked feather carbon for some reason. I might repack that one at the end of the video just in case. Wasn't quite packed enough. So about 12 ohms here. Yep. Oh, we're down to 11. And I reckon if you packed it more, it would probably be a bit more conductive as well. It's only in an open tube PVC dried. Been using this extension bar to pack it. Alright, I'll get back, and I think the next one will be wood carbon at 1000 degrees, which was in the fast burn of the feather carbon. Okay, standard homemade wood carbon. It's been put in the furnace a couple of times. Last time was with the feather carbons to suck up some of the fumes. That's just your standard bits of wood turned into charcoal. Got it packed in the cell. And for its resistance, we're looking at 2.9 to 3 ohms, sort of roughly packed. That's a bit better than the shop bought activated charcoal as well. So that's looking good, just for standard bits of wood chopped into small chunks and carbonized in urea and feather mix. So 2.8 there, 2.7, that's looking also not a bad carbon, but depending, the surface area may not be all that great. Resistance is high, doesn't mean the surface area is any good, but I think it's, I'm not sure what sort of, it's a splintery wood before it starts off. And if I can break the piece off, it's shiny all the way through as well. And the next piece is the shop bought charcoal, which was also in the feather mix at high temperature. So I've got it ground up here. So I'll pack that, sit and get back. Okay, what we have here is the shop bought cooking charcoal activated with urea and feather carbons. I took a slice. I wasn't expecting it to be all layered like that inside. Cutting through that distance with the hacksaw wears the hacksaw blade out immensely. It's like cutting through stainless steel actually, for the damage on the hacksaw blade. I was going to try to make an electrode out of that piece there. So its resistance over that whole area is 1.4, which ain't too bad actually. And on its other side, it's sort of got a silvery coating around the outside of this. Its resistance is down around about the same, 1.3 ohms over that distance, and I've got it packed in here. It actually packs quite well. It's one of the better carbons out of all of these so far to pack. It's not collapsing, and its resistance is slightly higher than its biscuit form, maybe due to its density of how I pack it. I'll just push heaps of weight on there. Alright, so it's 1.7 or 1.6 there, and on the solid biscuit it's down to 1.9. So the more you compact this carbon, the better resistance you're going to get. So this one here is looking overall pretty well, because most that sort of, you can make that in abundance. All you have to do is chuck some feathers and urea in the mix. It's just standard cooking charcoal, so it's not going to be activated anyway in the first place. And I think they just layer it up with whatever biomass they have, by the looks of that. Unless that's separating in the process, not sure. I think they'd pack a tube full of their carbon, then dry it. So, not too bad results. Looks like it's a toss-up between feather carbon, 4 hours at high temperatures over 1000 degrees in a steel crucible yields way better results in conductivity, and also the shop bought cooking charcoal was inside that same container, which is gives you abundant amount of charcoal, or carbon in this case now, and fairly resistive. Yeah, very good conductor of electricity. So I hope you find that video interesting. I certainly did. I thought the other feather carbon at slower temperature would be alright, but that one could be up on its surface area compared to the other one, which I'm not quite sure how to test yet. I was thinking of absorbing some water with a certain amount of grammage of the carbon might be a good way to test surface area. Alright, so I'll do some microscope slides of the carbon in its native form of the various carbons and put the images on the end of the video. And thanks for watching.